So we are kind of continuing from last week, moving past transistors. We're now going to branch off one level and now start to look at MOSFETs. We're going to look at the two primary N channel and P channel. Same thing as it was with the NPN and PNP. They can basically achieve the same operation. They can be used in similar applications. They have a slightly inverted use case to one another. To start, for either FET, what differentiates them from the transistor is that they are voltage controlled devices. Where the transistors were current based. So they needed to see some current on the base to amplify out to the collector, where you just have to apply a solid voltage to the gate of the MOSFET to activate the MOSFET. Typical looking at the NFET. Another 3-pin device where we have gate drain source, which, like I said, when we apply a voltage to our gate, we allow our system to be activated, and we get current flow across drain to source when the voltage is applied. Now, one thing unlike the transistor is the MOSFET. Typically, its use case is for just being as a switch. It doesn't have the same characteristics that allow it to be used for amplification like the transistor was. So most applications that you'll see a MOSFET, it'll only be used for blocking or allowing current flow in a trace. You generally won't see applications where it's being used to amplify current or voltage in any way. So main use case. There is also two basic forms of a MOSFET, which is enhanced and depletion. You almost never see depletion, because in most applications, when you would use it as a depletion, you could use a PFET. In most cases, and they're just typically more expensive and just less well seen. So enhanced is what you'll normally see. That is when we apply a voltage to the gate. The device turns on. Where depletion just works in the opposite. When you don't send voltage to the gate, it's turned on. So when you send no voltage, when you send, how would you say it, ground to the gate, it gets turned on. But again, you almost never see depletion for various reasons, but it's primarily, it's just most often not used because you can use a PFET in those cases, or it's whatever the case may be. Questions on?
Oh yeah, sorry. Is there a depletion PFET that acts like an NFET?
I believe yes. Yeah, I'm fairly certain that both NNP have these forms. Yeah, you can do a quick check to verify, but I'm fairly certain that both do in fact. Anything else on NPET so far?
Wait, what exactly does enhanced do again?
Enhanced is how you'll normally see a MOSFET. So when you apply a voltage to the gate, your device turns on. So that is if you apply, 5 volts or whatever it is to your gate, and then you have whatever load. When you apply the 5 volts, current flows through your device. Because one thing that I kind of alluded to in previous lessons is that the MOSFET is basically a switch that gets controlled by your signal closing. So for an enhanced MOSFET, which is what you typically see, when you apply this 5 volts, it causes the switch close and the power conducts. Whereas in depletion, if you sent this 5 volts, it would actually keep the switch open, so it would block. Anything else on that so far? Is that reasonable?
How do these relate to the N and the P you were talking about before?
Right. So, like we saw for an NFET or quickest relation, the NFET closely relates to the NPN transistor, while the PFET is closer to the PNP. So slight straight across. The difference that we'll see is if we run back up to a NPN, we were considering, so this is your NPN, we were considering it very similar, where signal on the gate on the base toggled the switch to allow current flow. Similar relation happens to our NFET, where signal has to happen on our gate to toggle the switching of the drain to source. So these MOSFETs behave similarly to how transistors work in saturation. Because as we saw last time with the transistors, they have their 3 different states: saturation, active, and cutoff. Saturation is where they behave just like a switch. So so yeah, we can see that MOSFETs acts similar to saturated transistors. And again, drawing the closer relation between across from NPN to PNP. When we are actually looking at that, there is also another way to draw these. I think it's similar draw. These are both for MOSFETs. You can see them drawn in a couple different ways. Just so if you ever see this one, it's still an N-channel MOSFET. But again, to draw similar to the NPN, what we need to see is our gate has some threshold voltage that we have to overcome. The threshold voltage...
The arrow should be going out for the second one.
Oh, it is out.
Yeah.
Yeah, I used to always draw this one, but I don't know, recently. Regardless, yes, you can see it in either way. Same thing. Yeah, so the gate will have some threshold voltage you have to overcome, just like the transistors. However, the thresholds will typically range more significantly than the transistors, where the transistors were typically some 0.6 to 1.2. MOSFETs can have much higher. Typically, you can have logic level ones, so they'll be triggered off of 3.3 or 5 volts, all the way up to, if you get power FETs, they can take even higher voltages to be able to turn on. So whatever, plus 5 volts. I believe they can be some 10 volts or some, depending on how high powered of FETs you get. So as you get higher powered FETs, you can no longer use your standard pin from your Arduino or whatever TMS570, whatever your typical microcontroller is. You can no longer use it as your gate driver, which gets into more advanced. You have to then send a signal to a gate driver, and the gate driver boosts that. But regardless, you still have to overcome some threshold voltage. And for the NFET, what matters, just like the NPN, was that there's some positive voltage between your gate and much like how the NPN was. It wanted to see that positive threshold voltage between base and emitter. And because of this characteristic, what we will see is that the NFET will typically be used in low side switching. For all the same reasons that the NPN was. That is, you have your you have some load above your device, and your source just instantly is tied to ground, so it always has a 0 volt reference. So it's easy to, if your threshold is 3 volts, all you have to do is send it 3 volts. You don't have to worry about increasing your supplied gate voltage to overcome that threshold. Exact same way how you would see the NPN behave. Questions on? Make sense on how it ties to the NPN?
So if my source was not tied to ground, then how would that change? Like, let's say for some reason it was at 5 volts or something. How would that change the gate signal that I have to provide?
Yeah, so if we now have a case where for some reason this is 5 volts and then it carries on, if you still just attempt to apply 3 volts, so because your V threshold, you'll typically see it in a datasheet, something as such. It'll be your VGS, or it'll be VGS with threshold. It'll have that reference. So it's about overcoming the difference between it's coming from there to there. So if you're still only trying to send 3 volts, but for some reason you have a 5 volts on your source, you're sitting at -2 volts, your device will not turn on. So this will remain as an open switch. So you won't actually allow current flow through your device. So if for some reason we have this 5 volts, we would now have to send, say, 8 volts to your pin to be able to allow for this plus 3 volts, and your will now allow current. Now it can be something obvious or not obvious, similar to how it was used, how we could see it in the NPN as well, if we tried using it as a high side switch. So we instantly tied over here. If you had tried applying that 3 volts, since off the bat you have no current flow, it would try to close, instantly close, current flow, you see 5 volts, and then it instantly opens back up. So when sending a 3 volt signal, because initially it doesn't see the 5 volts on the source, so it'll think it's okay, switch with 3 volts, and instantly VCC will be attached to source because it has no voltage drop beforehand. So you see the VCC right away, instantly opens back up. So it doesn't work in any capacity. This is now getting scribbled. So that's the same reason as to why we saw last time how the NPN wasn't good for being a high side switch. Same thing applies to the NFET. It doesn't like being a high side switch unless you are overpowering your gate signal. And in most logic level MOSFETs, you can find in the datasheet that there's a VGS max of, I think it's typically whatever plus is 20 volts. So there is a limit to how much you can try to overpower to use it as a high side or in whatever application by applying a higher volt. So it's best to keep it in its more desired state, which is low side.
Is that a plus minus?
Yes.
Okay. Thank you.
Because again, or not, if you're sending it 3 volts and it's seeing 5 volts, you are technically seeing a VGS of minus 2 volts. So you can just as well cause damage if you have, if you somehow see a 25 volts on your pin and then you only try to send it at 3 volts. You're then going to get a minus 20 whatever, and cause damage.
I've also seen some applications where people purposefully put negative voltage on the gate to try and, like if your switch were closed before, to try and open it as quickly as possible. But that's not common at our level, usually for things like high power switching in a motor controller, for example.
Yeah, so that would basically be for priming your gate signal so it can behave quicker. All right.
Yeah. Especially for like IGBTs, which are like high power versions of MOSFETs. They turn off slowly, so sometimes they put a negative voltage to turn them off quicker.
Yeah, IGBTs are some. They're an interesting mix of both an NPN and a NFET. I think their actual composition is something similar to that, so that's what will technically be inside of the IGBT. Collector emitter. I believe that's what an IGBT actually looks like internally. So it's used at another higher power level as this, but it's got kind of mixed characteristics from both. But those are kind of well beyond what we will touch, so I'm not really going to touch that. But just for sake of knowledge, there is another very commonly used item that kind of mixes both MOSFET and transistor into another package. Now, another thing you will almost always see with your MOSFETs is the application of a pull up or pull down resistor. So you'll have some load, source instantly ground, and because you're shooting this like a switch, you very precisely want to know when your device is active and inactive. You want proper control over that. You'll typically see your gate pin, gets tied to ground. Again, like we said, for in the resistors, this can be typically 10K to 100K. It varies depending on what you want it to do and speed, or if you're just generally tying it down. But you'll almost always see a pull down resistor on your gate. Unless you have, unless your gate is being driven by your MCU pin that has internal pull-ups, pull-down, but then that's the obvious. It is still using whatever. But again, just so you have a predefined, always known, if you're sending nothing, this is 0 volts. So your device is left and so you don't allow current flow. Makes sense as why we see that?
Sorry, Jarod, can you go over quickly again what's the purpose of the pull-down resistor there?
Yeah, so in normal application, you're going to send it, or in your ideal case, you're sending it 5 volts or 0 volts, whatever it is, to turn this on or off, to allow or to block. But when you're not sending it anything, it can easily pick up noise or kind of not parasitic, kind of leftover voltage in a way. So your gate pin can pick up all of this noise. It can float. It can be easily influenced by just the capacitive touch of your finger. So it can pick up voltages and it can float. It can veer around all wherever it wants to go. And that noise may be able to surpass the whatever 3.3 threshold it has, or it may dip below the 0.7, low voltage threshold that it has, and it will accidentally cause your system to switch. So maybe you're not sending it anything and you are expecting it to be sending 0 volts, but it accidentally, the noise brings it above. All of a sudden, your switch closes and it's now conducting. So it's in a case where you don't want something like that to happen. By putting a pull down, the signal is always going to be, if you're sending it nothing, but there's maybe this little bit of current, there's this little bit of power from the noise, from whatever it may be, you now have a path for that current to go, which is ground. So this gate pin is always referenced to ground. So this noise won't exist. You're instantly just holding it at 0 volts. So you're always keeping it in its defined stay open state. Make sense?
Yeah, thank you.
Any other questions on any of this? Then that's the base of MOSFETs. So if we slide into the PFET now, like how that's again another same gate drain source. Arrow's just pointing out this time. So again, the PFET ties close to the PNP transistor. All the same kind of systems that we see up here are hold true. So I'm fairly certain the PFET also has an enhance and depletion. And again, it's not going to be used as any amplifier system. Its primary use is just going to be switching device. But this time, when you, much like the PNP, your gate to source threshold is going to have to be a negative voltage. So what this means is when you are sending it, if we were to have it in the same case, and you send it a 5 volts, then that's going to leave it open. Whereas with the NPN, when you send it a 5 volts, it would cause it to close. And then once you send it 0 volts or whatever to surpass the threshold, then it causes the switch to close. Your threshold voltage is going to be basically the same as the MFET. So whatever typical 3-5 volts, it can have the same power. You can find similar power FETs that require the over 5 volts to be able to toggle, just the same as the NFET. Or in this case, it's -3 to -5. So what this means is that, again, just like the PNP, you'll now start to see it, or its use case will be more as the high side switch. And then you have your low load. And then that's what will tie down to ground. So again, it's going to be exactly opposite to how we saw the NFET. So if we see 3 volts on our source pin, and we try to send it, and we're sending it 3 volts to its gate, this difference is 0 volts. So it doesn't want to close. It doesn't want to conduct. So what we have to do in this case is instead send some lower voltage, 0 volts typical. Now we can see a -3 volts difference. And now our device wants to conduct and power to flow down to our load. Questions?
So this is kind of what you were talking about before when you were saying depletion, how no voltage is sent to the gate, the device turns on, right?
Yes.
Okay, thank you.
Yeah, so like this PFET, how it has to see 0 volts to turn on, is basically what the NFET depletion is. Where, in that case, when you send it 0 volts, it will also want to close. So they can be seen similar, where they just want to act in their opposite behavior. So an NFET depleted is similar to a PFET enhanced, and then opposite, your NFET enhanced can be same to a PFET depleted. But again, the PFET, just like the NFET, depleted is not very typical. So you'll often just see it used in this enhanced region, enhanced mode. Any other questions on that so far?
Jared, I think your PFET needs to be flipped. So usually the source is tied to high for P, and then for N we tie the source to ground.
Oh yeah, you're right. I just um,
Yeah.
I haven't drawn like that in my notes too properly, but yes. Sorry. I mean, logic still stands exactly to what we were seeing. So if it's tied to VCC, it's obviously seeing whatever VCC, call it 3 volts. It's going to see 3 volts on the source pin right away. So that's that's what has to overcome. Anything else on this? So I know when we were talking about the PNP as why not to use it as a low side, it was kind of holding us up a little bit, a little bit of confusion on it. But does this make sense? How PFET, PNP are similar? Why you want it high side?
Yep.
Cool.
So for the NFET, when we tried to use that as a high side, we had to provide 8 volts, right?
Yes.
Is that right from before? Yeah, and then yes, it's tough because, for example, your microcontroller may not always have 8 volts available, right? Depending on your logic level, you may only have 3.3 or 5. But now with PFET, which Jared brought up, which is great, you only need to give a 0 volts to switch the high side, and that's easy to do. So it's much better for high side, the PFET, which is really useful. And a lot of times people like to use the PFET on the high side as a switch. So for example, that load in the bottom is your whole circuit, and then you're controlling the first switch before allowing any current to flow towards your load. So it's super useful to be able to switch a PFET easily like that.
Yeah, and yeah, so you're able to use either in normal cases when you're trying to switch. But yeah, the use of just being able to send 0 volts is super useful, because this can be, if you have a system that's dealing at much higher voltages or whatever, it's much easier just to be able to send a 0 volt instead of trying to be able to have to boost it up all the way.
Do we have a similar scenario? You know how for the NFET you had a pull down resistor? What would we do sort of in this situation?
Absolutely. So when we are wanting to have it go up to load, since you're again, we want to assume our normal operation is that the switch is open, that we're not conducting, which is when we see some positive voltage, and it's only when we see our 0 volt step we close it. So the easiest way to do this is opposite to the NFET. We have a pull up. So it's at the same, whatever this is, VCC, call it 3 volts, whatever it is, whatever the threshold is. So we'll see the same we'll see the same effects that the pull down had on the MOSFET. That is, our pin is always going to be referenced right up at 3 volts, so it wants to remain open. Any noise or capacitive touch that you may have isn't going to influence the device to potentially float into maybe open, maybe closed. It now has a hard defined, just keep it open until you send it 0.
So when the gate is at 3 volts, so then VG is at 3, and then VS is at also 3, I guess. VCC is 3 in this case?
Yeah.
So they're both at, so VG is 3, and then VGS is just VG minus VS, I guess, right?
Yeah, so our difference from this point to this point is just VCC to VCC, so we have a 0 volts on our gate to source, which is our threshold, and we saw that our thresholds wanted to be at some minus 3 volts.
Okay. And then we have to be less than that minus 3, right? Or less or equal to.
Yeah, so when we send it, so when we now send it 0 volts, minus your VCC, sends this 3 volt, we're now seeing minus 3 volts, which is exactly what we want to see. So we're able to switch on the device. Cleared all? So that's the general efforts of my actual teaching. Now, one of the actual applications we can see in that we currently use in the VCU. Down here we can see we're using an MFET as a reverse voltage protection. Gabe mentioned this in one of his embedded lessons. But what we can see, what we can see is we have our input voltage. So this is the 12 volts. And then it's going
other way.
Where do you have it coming?
Yeah, the left should be called 12 volt in or something.
Okay. Regardless. So that's your input into the board. And then it goes into the board, does whatever it has to. And then that's going up to ground. So when we have proper connection, so 12 volt ground, we will see 12 volts on the gate. Which allows the device to conduct. So we have current flow. And if we were to have this inverted, so we have ground, and 12 placed backwards. We're now going to see 0 volts on the device, on the gate, which is not going to be enough to, which obviously isn't enough to actually conduct or to surpass the threshold voltage. So opens, doesn't allow any current flow. Since we don't have any current flow as a full path from 12 to ground, since that path is broken, none of your devices, none of the circuitry on the board will then be damaged because it doesn't have a complete circuit. No current flow, you can't cause a short on your device. Does that make sense on how it kind of...
Yep.
Yes, this is interesting because it's useful in the sense that with just one component, someone can now go in and plug power in backwards. So like accidentally swap the 12 volt and ground wires, and the board will just turn off. Like it won't allow any current to flow. Whereas if you didn't have this little protection piece, that would automatically fry all of the components on the board, because you're putting a reverse voltage where all the components that aren't expecting to see negative 12 across them. So it's really useful. It's fun. If you want to play with the VCU, you can put 12 volts and ground on backwards. Then none of the LEDs will turn on, but just be careful.
Yeah, and when we kind of look at if we're to kind of do that up again. So this is your in, and that's your board. Now, if we remember, there was when we were talking about diodes, there was something else we could have done, which is just placing a diode in path, since it only wants to allow current flow in one direction. So if you put it backwards, it would block it. So again, your current path would be broken. The benefit to the MOSFET for the reverse protection, or one of the things you have to look into the MOSFET when you're doing this, is parameter RDS on. Most MOSFETs will have resistance of some 0.3 and even less ohms. So you can imagine the power consumption from the MOSFET isn't going to be high, because 12 volts going at 0.3 ohms isn't going to cause a large power drop, where the diode has a much more substantial power loss, or even when using MOSFETs, if you're looking for the intent of reverse protection, you want to find the MOSFET that has the lowest RDS on, so that you don't waste power in this protection circuit.
RDS on is pretty interesting. I'd say it's one of the driving factors for MOSFET selection these days, especially in power electronics, because you can imagine your power losses are I squared times R, right? So if you can decrease R, then you're losing less power, which means you're generating less heat, and your components have less likelihood of getting damaged. So this is 0.3 ohms, which is about 300 milliohms, which would be relatively high for a MOSFET where you're hoping to have a low resistance. And again, this comes down to cost usually. You want a lower resistance, you have to pay more money. And that's sort of a trade-off that we have to do. I remember on one of my co-ops, semiconductor representatives would have meetings with us, and they'd come to us and pitch their newest MOSFET. And it was always a competition from the different suppliers to see who could provide the lowest RDS-on MOSFET for us to pick. Because that MOSFET was going to go into a car that was going to be produced millions and millions of times to go like for sale around the world. So if they can get just their one MOSFET into that car, then they're going to make billions of dollars. And so they would come and they'd pitch, and they were trying to get to sub 1 milliohm MOSFET RDS-on. So it was like 0.0001 was sort of the bar that you had to beat. And I remember one supplier came in and they're like, "Oh, sorry, we already picked another MOSFET." And they're like, "Oh, you got sub milliohm?" And we're like, "Yeah." And they're like, "Fuck." So then they left and they lost the contract. But that's definitely the name of the game for efficiency, and it's actually defining of whole industries of semiconductors. So pretty useful sort of thing to understand.
Yeah, it's definitely one of the bigger thoughts of when picking MOSFETs, even in our application. Because you can imagine for the VCU, since it's being used as a reverse protection, it's always on. As soon as you power up the car, it powers on. And then that just stays on for the entire duration of the car being on. So it's going to be constantly just eating power. So if you have something that's such small resistance, not much power loss, it's not going to affect much the system. Power can go properly where it needs to be without being affected too harshly. But you can imagine if you mispick this and it has a much greater, 5 ohm or something, it's going to continuously just eat at the power, and it's going to cause a lot of losses. So even at our level, this is one of the good parameters to consider when speccing out FETs.
So does that mean for MOSFETs, when you turn them on, you care about the RDS on value? For BJTs, when you turn them on, we care about the voltage drop, usually like 0.7 volts value. Right? That's like the difference between the two?
Yeah, that's one of the things. Yeah, for BJTs, yeah, the voltage drop matters, and there's another parameter that's generally, I can't remember what the typical or what the there is another good parameter to look at for BJTs, but I can't remember what. But yeah, in a lot of applications, considering your power loss, so whether that be your RDS or your voltage drops or whatever it be, are generally critical to think about. Something else, I mean, we can also do this reverse protection with a PFET as well. So that's your in board. So we can achieve the same thing with the PFET as well. Again, it does the same thing because we're sending it 0 volt, so once it turn on, it goes through. And the only difference is you're throwing it on the positive rail instead of the negative rail. But we can see it'll operate the same way. So when you're doing something in this nature, you're not restricted to using only one or the other.
Yeah, both definitely work. In this case, usually for the same amount of money, MFETs usually tend to have a lower RDS on. They have less resistance when switched on than a PFET. All things equal, in terms of like money and build and cost, and that has to do with like the fundamental mobility of the electrons and holes down at the silicon level. But if you want to research that, definitely go for it. But this is just sort of a general rule of thumb. You can spend more money and get a PFET that has a similar or lower RDS on, but with sort of the same parameters in terms of cost and size. That's lower.
Yeah, there's some cases where MFETs are preferred over PFETs. I think PFETs also have some inherent slower reaction time, or it's slower response time. PFETs will have some minor differences in parameters like speed and stability. So there are times when to choose one over the other, but in most cases either could be used.
Yeah, some people say that PFETs also have lower noise when switching, but I haven't seen that used a lot as a justification. Even for things like everyone's electric longboard, little motor controllers, like on the VESC, they use all MFET due to the lower resistance, because you have a lot of current passing through that motor controller to run your longboard. And so even though, for example, we talked about how it's hard to use an MFET as a high side switch because you'd have to provide that 8 volts, what a little motor controller like that will do is go from your microcontroller to something, like Jarod said, that'll step up the voltage that gives you exactly what you need to turn on the MOSFET and move forward. So they've found that it's more worth it for the efficiency of MFETs to have that stage in between that steps everything up. And looks like Jarod is on it, on explaining.
Yeah. So if we wanted to look at typical kind of inverter layouts, those tie. Can I? No.
Do you want to just do an H bridge for now?
Sure. No, I don't want. So whatever load So yeah, if we go just load and then we say we're running maybe that's a great for 24 volt system. So we have 4 gates that we're controlling, so I don't remember how they typically lay them out. Where if you're wanting to drive this in an AC load, or if you want to, not even AC load, yeah, say our load is some just DC motor. By sending current this way, this puts it in forward. And then by swapping the opposite, we're setting it in reverse. So we can see that our, can I draw this? What am I doing? These are all.
Yeah, I think your 4 guy should have the source at ground, like the 2.
Yeah, that's what I was sure. We can see that our 4 and 2, those would be easy enough to control, because we can see source is directly tied to ground, so the your source has a reference of 0 volts, so that's easy enough to control. But the source on our uppers are 1 and 3. Since they aren't directly tied to ground, they go across a load. We are still going to see some 24, it maybe slightly dropped, whatever voltage drop may happen across the MOSFET or externally. But we can see that there will be some higher voltage present at the source pin before it goes across the load and then down to ground. So in this case, we have 4 PWM, or just general 4 signal pins that would be used for controlling our gates. Now, our microcontroller is only going to send 0 volts or 3.3 volts. 3.3 volts is obviously not enough to overcome this threshold if we have 3 and then we're dealing with 24 volts. We're going to have some minus whatever 20 point whatever volts it is. So our MOSFETs are not going to switch. Our upper FETs aren't going to switch. So instead of mixing NFETs and PFETs, which sometimes is done, some applications will just use PFETs on the upper sides, and then controlling is a little bit easier. But what is kind of more frequently seen when you're just dealing with 4 NFETs is your gate driver will be something to then boost your 3 volt to something more substantial, whatever the actual required gate voltage that needs to be seen. So now instead we'll be seeing an amplified, I think they're typically also tied, so it'll be like 24. Whatever it be, we now just have the 4 PWM, or the 4 signal lines, exactly as they were sent from the microcontroller, just amplified. So that they will have the whatever necessary 24 plus volts that are required to actually switch the highers as well as your low sides. Since the low sides, they're not going to matter as much because they were fine with 3 volts. Setting them 24 volts is going to work just the same as long as they are properly spec'd, that your whatever gate threshold is greater than whatever gate you're trying to send it. So in most H bridges, that's already consideration that all 4 will, or when you're if you're designing an H bridge, that's a consideration to think about, that all 4 have to be able to tolerate all these voltage levels. Does this make sense to people? Questions on how that functions?
Doesn't it take more power if you don't, like, what's more typical, like 4 MFETs or 2
I think it more matters on the power levels of your switch, of your H bridge. If it's running on the lower voltage side, or you're not really caring about efficiency, I think the mix is more common. But when you start to get to higher, so assume not 24 volts, but we're now maybe thinking 200 volts. This is now something that's going into a go-kart. Power considerations are much more prevalent. That's much more required. So you're now going to start optimizing for power. And like we said before, the MFETs are typically cheaper to achieve the same. So mixing all of your MFET or solid to all MFETs may be more typical. Anything else? That's maybe not from Gabe or Andre, since they've been the only questions, really. Nobody anything? Okay. That is all I had for today. A little bit more of an application onto what we actually use these for. And we'll kind of deep dive another use case, which is, switching power converters a bit later. But that's it for this session if we have no more questions. Actually, I'll pull a Gabe. I want 3 questions before we can end this.
Can I ask one?
Ask one.
Both BJTs and MOSFETs are used for switching, but
Okay.
BJTs can do amplification. Why would you choose a BJT over a MOSFET and vice versa for switching? Like, why is it more common to see it for switching?
MOSFETs are better at handling higher power. So again, with the RDS on being incredibly low, they typically have better power dissipation or power handling in general compared to BJT. Then I believe the operating levels of typical BJT is lower than a MOSFET. So if you were to run it at trying to run the same power, you'll be able to find MOSFETs can accomplish the switching functionalities at a cheaper rate than a BJT would be able to achieve the same power. So I believe it mostly boils down to power, power dissipation, power handling, and all that such. Two more. Can be on the MOSFETs and or the transistors from the last week's lesson. I was about to say, Raphael, just bailing on us. Avoid the question.
What? I'm here.
In another class I was in, they were like saying something about it like boosting the voltage, and that's like another good thing about MOSFETs is, I don't know, I just don't get how that works.
For boosting voltages?
Yeah, something like that, or current. I'm not sure.
Well, I mean, the MOSFETs will be used in boost converters. Inherently, a MOSFET on its own, I don't believe has any amplification powers over voltage or current. Gabe, maybe correct me if I'm wrong.
I think what they're trying to get at is, like, for example, like if you draw a circuit, just like with the low side NFET switching a relay at 12 volts, but like with 5 volts control signal, for example, you can control a 12 volt load. Maybe this is what they're talking about.
Yeah, that might be the... Yeah, so if you have a relay that drives 12 volts, you're able to switch something that requires 12 volts with only 5 volts. So yeah, that's one of the nice things. Since this source pin is always, if you're using it as low side, it's referenced to ground. So that switching will always, that threshold will always be satisfied with the 5 volts. So as long as your MOSFET can handle higher voltages, you can be controlling 60 volt circuitry above your FET, and only control it with a 5-volt signal. So that's one of the benefits.
Oh, okay. I think that's what it was. Thank you.
Final question.
Do we usually use H-bridges as ICs, or do we design it ourselves?
Typically, for most low power, yeah, if you're under 24 volts, you're basically just going to buy an IC for it. Only when you really start to get to higher powers, you'll design your own, purely because to achieve the same power kind of management, consumption, handling, whatever you want to call it, it just needs more. It needs more space. It needs bigger MOSFETs. It needs more thermal considerations. So you just can't nicely put that into an IC. So typically at low power, you'll just buy the IC. You'll send the 4 pins. It's 4 control pins. That's it. But when you get to higher power, that's when you start to design your own. Okay. That does it for the session.